It sounds like science fiction, that extra dimensions. But actually, there are many signatures of those extra dimensions that we can see at the Large Hadron Collider. And this is just one example. What can happen is you can collide particles together at the LHC, and you can create particles called gravitons, which carry the gravitational force. And they would, more often than not, disappear off into the extra dimensions, carrying lots of energy away with them as they went. So one of the ways you can look for extra dimensions at LHC is look for energy going missing in the collisions. Quite literally, you bang two protons together and a load of it just disappears. And we've calculated what they may look like. So it could be, on the more speculative end, that we'll discover in this kind of Copernican revolution all over again, that not only is the Earth not the center of the universe, or the Sun not the center of the universe, or the Milky Way one of billions of galaxies in the universe, but we're one of hundreds or billions, or perhaps an infinite number of little sheets floating around in a higher dimensional infinite universe. So that would be a remarkable thing to discover. It sounds like science fiction, but it's not actually as speculative as it sounds. So just to finish, before I open up to questions, let me just say a couple of minutes about what I think the value of this project is, because it all sounds a bit esoteric. You know, I've talked about small particles and extra dimensions and studying the forces of nature, mapping the universe. What use is it? Well, of course, it's been profoundly useful. I mean, our modern civilization is built on the fruits of research from decades ago, centuries ago, hundreds of years ago. It's obvious. Even today, the spin-offs, the World Wide Web, for example, which was mentioned earlier, we're streaming this on the World Wide Web now, that was invented at CERN. Why? Because it was necessary to do particle physics. So it wasn't invented to build Amazon.co.uk or something like that. It was invented to do particle physics, and the spin-off was, well, the modern World Wide Web. But that's, I think, kind of a side issue. It's obvious. It's obvious that exploring the universe delivers great technological benefits. I think you'll hear some from the shuttle astronauts later, the benefits of the space program, what it's done for us. But I think there's more than that. What I want to focus on is the story that it's taught us, the cultural story, if you like, about the universe and our place within it. See, I mentioned earlier, we've got this astonishing picture now from measurements that were made only in the last few decades. A picture of a universe that began, as far as we can tell, 13.73 plus or minus 0.12 billion years ago, and began to expand and cool. We've got some strong evidence that something like a millionths of a second after the universe began, it underwent an exponential expansion. It's called inflation, which grew the universe from something smaller than the size of a single atom to the entire observable universe that we see today. And I mentioned that we think that perhaps the origin of the seeds of the galaxies, the formation of the galaxies, occurred sometime before that. The universe then continued to expand and cool. We know very well that something like a billionth of a second after it began, this mechanism kicked in, which may or may not be this thing called the Higgs mechanism, which gave substance to the particles in the universe. So the electrons and the quarks that make up our bodies entered the universe and got their mass as we know them at that time, a billionth of a second after the Big Bang. Why? Because we can do experiments there. We're then on very firm ground. From a billionth of a second after the beginning of everything, we're on firm experimental ground. So we know after about a second that the universe had cooled enough for the quarks and the gluons and all those things to stick together into the first elements, hydrogen and helium. And after about a minute, we know that the universe was about 75% hydrogen, 25% helium, which is roughly what we see today. No other elements to speak of present. We then know that the universe continued to expand and cool. We know that, as you see here, after about 400 million years, then the first stars formed. They began to cook those lighter elements into heavy elements. So shortly after that, the elements like carbon and oxygen, the building blocks of life, entered the universe for the first time. We understand that process in great detail. We then know that the universe continued to expand and cool. The first generation of stars lived and died, threw those heavy elements out into the universe, and in our corner of the universe, a cloud of those heavier elements coalesced and condensed into our solar system. And it's worth remembering that on only one planet that we know of, in the universe at the moment, those heavy elements that had taken billions and billions of years to form, got built into structures like us. So life, simple life, and then complex life. Life that can take pictures like this. It's worth remembering. This is a picture from Apollo 17 back in 1972, before you were born, but one of the most iconic images of planet Earth. It's often said, actually, that images like this famous image called a blue marble, actually were the beginnings of the environmental movement, because we stepped away from the planet for the first time. We looked back at it, and we saw a planet not as this indestructible thing that we have a right to treat as we wish, but as a rather more fragile thing hanging against the blackness of space. But I think it makes it even more remarkable when you see that we've learned this story about how it got there. The story is not that this thing just appeared and we appeared on it. The story passes back to events that happened less than a billionth of a second after the Big Bang. And I think to leave you, I think one of the great cultural values of exploration and science is that we can tell stories like that. It places us in our place in the universe, makes us rather more valuable than I think many people think, because we are, as the great Carl Sagan always said, the product of 13.7 billion years of cosmic evolution. Actually, there's a great part in his television series Cosmos, which I recommend you look at if you've never seen before, where he turns to an image like that and says, this is the thing that hydrogen atoms do when given 13.7 billion years, which is a wonderful thought. So let me leave you with this. Actually, I was talking with the astronauts you're going to hear from in a moment last night, and we're talking about how we continue to make sure that exploration, scientific discovery, the telling of stories like that, as well as all the useful stuff, is valued. And I remembered a quote from way back, actually, from something like 1800, from a scientist, Humphrey Davy, who was one of the great advocates for the value of just curiosity-driven exploration of the universe, asking the biggest questions you can ask. And he was challenged by a politician, I think, to justify that quest, right, to justify the doing of science. And he said something that I think really resonates today as much as it resonated back in 1800. He said, the reason you do science, you explore, is that there is nothing so fatal to the progress of the human mind than to presume that our views of science are ultimate, that our triumphs are complete, that there are no mysteries in nature, and there are no new worlds to conquer. Thank you very much. Question time. Oh yes, it's time for questions, I believe.
Well, thank you for that, and I'm sure, well, the silence told everything. Everybody was mesmerised and listening very carefully to the wonders of what you told us and how we are where we are, and what will the future bring? That's the big question, isn't it? I have questions here. We've got about 25 minutes of questions, if we can get through them all. The first one I've got, I'll only ask the question where we've had one from a school and there's no name. So the first one is from Queen Elizabeth's Secondary School, and the question is, who is your scientific hero and why?
So, who asked that? Do you want to say, where are you? Which school is it? Just say the school.
Queen Elizabeth II. Just show where you are.
One of the quiet ones. All right.
They've gone quiet now.
I have two, really. One who, again, I would recommend that you read both of these people's books, because they're incredibly fascinating books. My scientific hero is probably a man called Richard Feynman, who is a very famous, charismatic and brilliant physicist from the 20th century. He did his great work in the 50s and 60s, 70s, worked with NASA actually on some inquiries into the space shuttle towards the end of his life in the 80s and 90s. He was an interesting physicist because he roamed, his imagination roamed across vast areas of physics. He won the Nobel Prize actually for something called quantum electrodynamics, which was the first prototype theory that went into the standard model of particle physics that I showed you on one of those slides. So I think for many physicists he's an iconic figure because he was a genuine, curious explorer, and great results came. In fact, particle physics is done with something called Feynman diagrams to this day, so that's the way you calculate the things that we see at the Large Hadron Collider. But the other great physicist, I think, and I mentioned him as well, was Carl Sagan, who, as I said, made an iconic series in 1980, actually, called Cosmos, which is still relevant to this day. He wrote a wonderful book about the series, many other books as well. And Sagan, I think, is one of my heroes because he was a great humanist and popularizer of science, and spent a lot of time actually talking about the value of science to our civilization, and it's something that I think we need to emphasize and continue to emphasize, and Sagan did that beautifully.
Thank you. If I can now go to Stephen Isherwood from St Ninians High School. Stephen, you have a question.
If the universe is expanding, what is it expanding into? What is outside the universe?
It's a great question. I get asked that question a lot, actually, because it's the obvious question to ask, which makes it a great question. The standard answer, the orthodoxy, is that space and time themselves began at the Big Bang. So this is Einstein's picture of the universe from 1915, essentially. So if you think that space and time began at the Big Bang, then it's space and time that are stretching. So all of space and all of time were there at the start. You can't have anything outside of space, because space began at that point, and it's just stretching and stretching and stretching. And that's the standard picture of the universe. So the answer is there's nothing for it to expand into because there's no space. However, so that's the standard picture. And I admit that's difficult to picture, but that's the standard answer. And the other thing I talked about briefly about these extra dimension theories suggests that indeed there could be more space than we can see. So we're a little sheet in a bigger universe. And then you can imagine our sheet expanding and expanding within that larger universe. I imagine this room as being the larger universe. And actually that's one of the speculative explanations, as it were, for what happened before the Big Bang. Because again, the standard answer is, well, time began at that point. So you can't ask the question what happened before. And that sounds like a bit of a dodge, but it's the standard view. But actually, in these extra dimension models, a model for what happened at the Big Bang is that two of these sheets of space and time bump together. And you can calculate what happens when they bump together. They become very hot, and the matter and energy distribution on them becomes very dense. They separate away from each other, and they stretch and expand as a result of that collision. And that's actually what we see. So you've got to remember that the data, the experimental data, is that if you look far away, so you look back in time, then the universe is hotter and denser, and it's been expanding ever since. So that's the data. So that actually fits. So these models fit the observed data. So it could be the universe has been around forever, and our sheet is stretching into the extra dimensions. Or it could be that the universe, space and time began at that point, and it's space and time that are stretching. It's not expanding into anything. So.
Good. Okay, thank you. And then we've got Michael Perry from Castle Rushen High School. Michael.
When did you decide that you want to get involved in high-energy particle physics?
Actually, I knew that I wanted to be a physicist, or actually an astronomer, or something to do with space exploration or space flight from when I was very little. Right? I'd been interested from as far back as I can remember. I was born in '68, so I grew up at the very tail end of the Apollo program, which I don't remember, but I watched the moon landings. I was always captivated and fascinated by that. But when I went to university, I started doing astrophysics. But actually then discovered, and this is what happens when you go to university, that there's a whole area of stuff that you didn't think of. And I didn't know particle physics existed, really, when I went to university. So it captured my imagination and I moved, and you can always do that. So I think the key thing is, if you think you want to be a scientist of any description at all, is to remember that the path that you finally take can be broad and different. You don't need to make up your mind. You just have to make your mind up that you want to be a scientist, so that you do the GCSEs and A-levels that you need to get to university. But there's a lot of flexibility within that. So yeah, it was at degree level. And I'll tell you just one extra thing, actually. The reason that I thought that I was surprised that I went into particle physics was I thought I couldn't do maths. That I really found maths very difficult at school. And I discovered subsequently that it's about practice. And it's like saying I'm going to sit down at a piano and just going, I can't do that. You know, you know that a piano or a guitar, you've got to practice a bit to learn. Most people have to practice at maths. And so I really went into astronomy. Astronomy colleagues won't like me for saying this, but astronomy is rather less mathematical than particle physics, certainly observational astronomy. So one of the reasons I thought I'd do that was because I thought there'd be less maths in it. And then at university, I found that I liked doing maths, and I could actually do it, and then went into theoretical physics and particle physics. So I kind of changed on my route through university.
Right, thank you. And we have now one from Callum Cairn from Ballacomene High School.